So good morning. Today we'll discuss data dimensionality reduction techniques in this talk. So our ultimate goal is to find a pattern for a higher dimensional to lower dimensions without without original data information. So that is the main intention of for a higher dimensional data to lower dimension. What is that basic idea is a dimensional reduction in a machine learning models. The machine learning model, the classify as a four types of models, whereas supervised machine learning model, unsupervised machine learning model, semi-supervised machine learning model, and also the last one reinforcement machine learning model. The semi-supervised machine learning model is a combination like supervised and unsupervised. So look at supervised location. Supervised machine learning model is nothing but we have a labeled data. So that means the function of data is xi comma yi. We look at the data points xi comma yi. We find the yi value. Yi is a regressive value. That means yi belongs to real values. So that is a regressive, but prediction purpose, most of prediction purpose, supervised learning model, and also classification. So if you take a logistic regression, yi belongs to 0 comma 1 only. So that means we have a labeled data. Those labeled data regressive and classification purpose we can apply supervised learning model. Whereas in unsupervised machine learning model, there is no data points. There is no regressive points. Only xi data is there. There is no yi points. That means there is no labeled data. That purpose we can cluster the data. The clustering is a different types of techniques are associated. One of the clustering dimensionality reduction, one of the important weapon of the to apply futures, to apply better future engineering for machine learning models. That purpose dimensionality reduction techniques is a look at to dive into the picture in unsupervised learning models. So whereas the third one semi-supervised, the data is consist of sometimes a labeled data, sometimes unlabeled data. We can find a semi-supervised machine learning model. So whereas the fourth model, reinforcement machine learning model. Reinforcement machine learning model is one type of supervised machine learning model, but we have a risk and reward also is associated in reinforcement risk. So previously in supervised only we can find a prediction, regressive and classification. We cannot discuss risk and rewards. So we discuss risk and rewards based on the policies, based on the actions we discuss in a reinforcement model. So whereas in this talk we mainly focus on data dimensionality reduction techniques. So many techniques I collected from beginning 1901 to 2020. So whereas to be, I offered a course for with respect to undergraduate and postgraduate and PhD students and real-time experts. That's why I collect from basic fundamental to latest techniques. So whereas to convert deep dive into data dimensionality techniques, the first technique is the principal component analysis. The principal component analysis, here the four words I am using, three words mostly, the global data preservation, local data preservation, it's a linear or non-linear algorithms. So what that meaning of every algorithm has to be, the basic idea is higher dimensional to lower dimension. And also we can find a data preservation. That data preservation we can focus on global or local. The principal component analysis is mainly focus on linear algebra model. The linear algebra, what is the importance of linear algebra in machine learning? In linear algebra, we can associate it with data dimension purpose. So whatever the data is there, the data is converted into a vector format. So that purpose we can use linear algebra concepts, and also data dimensionality reduction purpose, and also we can matrix transformation. We call it as matrix multiplications purpose. So we are using mostly linear algebra concept. So one of the idea today's class we discuss principal component analysis. The principal component analysis is a very simple idea. We have a data points are there. Those data points we can standardize the data, maybe column standardize the data. So that means we can every column mean is 0. The first of all, whatever the data is there, those data we can convert as a standardized. So standardized means unambiguous information we can remove. Then we can find a covariance matrix, one type of matrix we can convert. So those data matrix to convert as a covariance matrix. Once covariance matrix is when you are converting to find its eigenvalues and eigenvectors of that covariance matrix. What is that meaning? Here we are finding a projection or direction of the data. That is a very simple idea. That purpose we are finding eigenvalues and eigenvector. Eigenvector will give the direction of the data. So that is the basic idea of the principal components. So what is the principal component here? Eigenvalues or values are more. That means lambda 1 value is more, lambda 2 is more. So more values information, that means that has to be more information is preserving. That is the basic intention of principal component analysis. Like that, the after 100 years, another algorithm, the phenomenal machine learning expert Jeffrey Hilton is designed TSNE model. So this model is a more accurate than principal component analysis. So this model is working on local data preservation. So it is also non-linear model. It's a combination of perfect slate models. Perfect slate, they are applying some probability concept and graph theory concept. They can find more visualization than with respect to PCA. We'll discuss one by one in coding also in this class. So next one we discuss a large vis graph theory. This is a graph theory model completely. So only they focus on local data preservation. It's a 2016 they are finding. In 2018 is a mathematician Leonard McLean's. It's a powerful model they are discussing, UMAP model. The TSNE has some drawbacks are there. They identified, they figure out some new model is invention. So they can apply some more modified and topology and fuzzy graphs. They can inherently to apply more accurately than TSNE. So that is also linear model. So these models only we look at local data preservations. So in 2019 they can figure out both preservation, whereas to be global and local. The Ian Ahmad is designed some tri-map model. So that is a simply a graph theory model. It is also to preserve global data and local data in this context. The last one, the foremost one, the nowadays all companies are using the PSE map, pairwise controlled modified approximation. That's a look like extension of UMAP. So UMAP algorithm, some drawbacks are there. You don't find global data preservation. So that is also they can find by applying a topology concept and graph theory concept. So Yang Fin Wang is design global data and local data preservation. They can find the best patterns for a higher dimension to lower dimension. So one by one we look at my talk will present as the whatever the algorithm will discuss. The first we get geometrical intuition, next one mathematical intuition, next one programming intuition is there in all my classes and programmings. So that's why the first we look at the PCA. The PCA is one of the fundamental model. This is published in 1901. This is the original research paper. Is a London Mathematical Journal. They published in that's Carl Pearson is discussed this model. So look at one by one in this. So what is that PCA? The principal component analysis. We are finding the principal components. The value is the very simple idea is the maximal variance. The maximal variance are equivalent to the maximal value of principal components. Here, this is the idea, the fundamental idea. So what is that here? See this one. Our idea is higher dimensional data, X. That is n observation, 1, 2, so on, n observation. So that is a d dimensional. So d dimensional, the future one, so on, the future d. So n cross d. So that belongs to xi, your data matrix points belongs to the real number of data points. This is a higher dimensional data. So what is your transformation? Your transformation, we call it as transformation. xi, your projection data, So 1, 2, so on, n, the future 1 and the future 2, let's say n cross 2. Mostly future 1 is a projected data. The one interesting question in a lot of interviews by applying PCA, so your data points, D points are D-dimensional, that is a D-dimensional data points. So you are transforming D dash dimensional, the same data points here, for example, same data points when you are using or not. So that is not. Why? Because it is not a subset data. We cannot use subset of D. The very simple thing, we cannot use subset of D. The first observation. Second observation is a projected data. We are finding projected data. The D dash data is projected. It is not a subset data. That is very important observation when you are applying a PCA. The most important questions, most of our product-based companies asking like that. So what is that? So the first we look at the two-dimensional convert into one-dimensional, less n-dimensional to that. For example, I have two features are there. So for example, diabetic data. I can take a diabetic patient's data, futures data. So this is a weight, this is a height, mostly height. So I can figure out some data points. Let's say data points. That's data points. So what is the PCA? What is the PCA idea? Basic idea of that. Maximum variance has to be data, more data is preserving. The first step, we can find variance. The variance are spread of F1, F2. The variance means this is the data variance. So this is where of F1 is, this is where of F2. Yes. So when you are observing this data, the variance of F2, the complete less than variance of F1. So that means your data, the more data is preserving here, F1. So now we skip the F2 data. Only we can apply F1. So now your data matrix will convert, like for example, I can transform the data like that. For example, so on n, the future 1 and the future 2. So n cross 2 future, the transform to x dash like that. 1, 2, so on n. The only the future 1, n cross 1. This is the way a two-dimensional data to convert as one-dimensional data. The very simple data set point. This is the very simple data set points. Very simple way. Only simple way means variance. The more variance, or simply we call it as a maximal variance. Has to be more information stored. So that is a fundamental idea from two-dimensional to one dimension. Whereas to be, for example, if you take the data points are like that, I can take the data points. For example, another model, I can take data points like that. So previously there is no data point. So here this is a future one, this is future 2. So how to find the variance of this data? So it's a very simple idea. This we can write a projected line. This is a F1 dash projection. This is F2 dash. F2 dash. So that is a transform some theta. Like that's a projection will give the information about the data. That purpose we are finding the model. We are applying a model, the PCA model, for using projection idea. So what is that here? For example, a d-dimensional data is there, d-dimensional data, to convert as a d-dash dimensional. This is the ultimate. The one example I discussed, 784 dimensions. Already so many people are using MNIST data set to convert as a two-dimensional visualization purpose. Two-dimensional visualizing purpose. So what is that process? The process involves PCA algorithm. We'll look at the first one. The first PCA algorithm, the steps, nearly 4 steps involved, but it's a manual steps. So in programming only single step is enough. The first we can find what is that, we can standardize the data. So that is a S matrix. The step 2, whatever the standardized data, the standardization means the mean of column standardized equal to 0. That is, once you standardize the data, we can figure out the we can convert. That is a not finding, the convert covariance of standardizing of that data. So that is, we call it as a covariance matrix of that standardized data. Once you standardize the data, the covariance is matrix when you are converting to find its very important thing, eigenvalues. Why eigenvectors? So this is very important phenomena we'll discuss in a later point. Why eigenvalues or eigenvectors are very important in this PCA algorithms, and also very important for data representation also. So once we find the eigenvalues and eigenvectors of covariance matrix, the step 4, to identify principal components. The principal components identify the maximum eigenvalues. The eigenvalue is more. That is principal components. We identify the principal components. So once principal component identify, we convert higher to lower dimensionals. So that is the model of PCA algorithm. So we look at one by one in a programming way. We look at. So I open my notebook, Jupyter notebook.